Okay, here we are in 4.6. It's our last section of Math 60. You guys have just been such hard workers and you've pushed through. I know these videos take a lot of time and effort to kind of comb through, but for those of you who are using it as a learning tool, I hope it's been beneficial. So here we are in 4.6. Hopefully you're feeling like you've got linear equations and graphing kind of under your belt. And you're becoming that expert grapher from equation to graph, graph to equation, back and forth. If not, you might want to wait on linear inequalities because you want to get really good at graphing the lines and then jump into the inequalities. Or some of you might know that maybe forcing yourself to go through this will help solidify some of the things that are still iffy about linear equations without the inequalities. So just be aware that if you get stuck a little bit along the way, we're going to use our graphing techniques. We're just involving now less than, greater than, less than or equal to, or greater than or equal to, instead of the equal sign. So it means our graphing techniques are going to remain the same. We're going to add one more piece to that to be able to do the inequalities. Let's recall what it means to actually be a solution to a linear equation. So when you have y equals mx plus b, or if you have ax plus by equals c, or you have y minus y1 is equal to m times x minus x1. These are the three forms of a linear equation. We've got our friend, our formal, our fallback, slope-intercept, standard form, point-slope form. Three forms to a linear equation. A solution to that linear equation is a point on the line that these equations represent on the graph. Another way to talk about it is it's an x-y pair, an ordered pair, in fact, xy, that works in the equation or makes it true. So that's what it means to be a solution to a linear equation. So let's look at a quick example of that. If I had this line right here, which, by the way, if we're given this line and I asked you to write the equation of this line, our goal would be to fill in y equals mx plus b, this one right here, because we can see the y-intercept of 0, -3, and we can count off the slope. We notice that it also crosses at 2, -2, and it also crosses at, it's hard to tell where it crosses here, but it definitely crosses at 2, -2. So we have 2 points here. We have 0, -3, and we have 2, -2. And one of the points we were able to identify was the intercept, so there's our b value. We can figure out our slope by going from one point to the other. First by the rise, it's going to go up 1. So rise over run, the slope of this, up 1, and then to the right 2. That translates to +1 over +2. So our m value is 1/2, our b value is -3. This equation is y equals mx plus b, 1/2 x plus a -3, or just -3. So that would be the equation of that line. Now, what does it mean to be a solution to that linear equation? So all the points on this line, every single point that you could identify the xy coordinates for, and some of them we can't tell by looking because they're going to fall in between the grid lines. But every point that makes the equation true, every xy pair that works in this equation, you plug in for x, plug in for y, and you get an equal true statement. Those all are points on the line. So all these points, infinite number of points connected together that extend both directions here on this line, make this equation true. That's what it means to be a solution to a linear equation. Okay. Now, what we'll recall is we've already solved inequalities. We have, and this was in 2.6, we have solved, say, like 3x plus 7 is less than or equal to, let's go 1. Okay, and we solved that. We solved it like an equation. We subtracted 7 from both sides. We got 3x is less than or equal to -6. We divided both sides by 3, always watching for the red flag would be if we would have multiplied or divided by a negative, it flips the inequality. But in this case, we're dividing by a positive, so it doesn't flip. We're left with x is less than or equal to -2. And we said, okay, what does that mean? That means that on the single dimension number line, here we are at -2, we want all values less than -2, and we would identify that we would include -2 because of the equal sign with the bracket. And we also learned about interval notation where we said, okay, it goes from -infinity to -2. We're including -2, but we don't get to include negative infinity. So this is interval notation. Here's the number line version of the answer. Here's the inequality version of the answer. That's what we did in section 2.6. That was with one variable. So now what we're talking about is the solution to, so the recall is really here, what we did with one variable. Now a solution to a linear inequality in 2 variables is what we're talking about now. So similarly, before this chapter 4, before we started working with linear equations that had 2 variables, x and y, we were just doing things like, let's say, -3x plus 2 is equal to, oh gosh, let's say 14. And then we would solve that, and we'd say, okay, subtract 2, and you'd get -3x is equal to 12. Then you divide both sides by -3, and you'd get x is equal to -4. You'd get a single answer when we had one variable. And if we were to plot that on a number line, it would be, you know, just the dot at -4. It'd just be one single value that we could plug in and make this true. On an inequality with one variable, this shading means that we could plug in any value. We could pick any value to the left of -2, including -2. Plug it in, it would make this true. And any value to the right of it, you could not plug in and make this true. So if we landed here, say at -5, you could go 3 times -5 is -15, plus 7, that's -8, and indeed that is less than or equal to 1. And you get bigger or smaller, I mean, as long as you stayed in the shaded area, you had a true answer for this. Same idea now that we're talking about a linear inequality in 2 variables. So now we're talking about, and you'll see them in all kinds of versions. You'll still see the formal. So ax plus by and c, and it could be less than, or it could be greater than, less than or equal to, greater than or equal to. You'll see the friend version. Y equals mx plus b, that's going to be your easiest one to graph, and instead of equals it's going to be less than, or it's going to be greater than, less than or equal to, greater than or equal to. You won't necessarily see it in point slope form. That is really beyond what we would need to do for this time around, so you'll really see it in either the formal or the friend version. But basically the idea remains the same. It's the point, let me get a better color here. To be a solution to a linear equality means it's a point on the line or on one side of the line. Or you could rephrase that as it's an xy pair, meaning an ordered pair xy, that makes the equation true. It works in the equation. You can plug it in and you get a true statement. Okay, so what does that mean? That means that when you have this line right here, when we were just solving for the equation, every single point on the line worked in the equation. But when we're talking about an inequality, now you're talking about not just on the line, but the line is what divides the two sets of solutions that will work. Either all the points above it will work or all the points below. Kind of like on the number, exactly like on the number line, we just had one dimension here, either all the numbers to the left or all the numbers to the right of that particular point. would work. So now we're looking for all the numbers either above or below the line that will work in this equation. And whether or not we include the line will be determined on which sign we use. So if we use less than or greater than, the line is not included. The points on the line are not included. So the points on the line are not included. If we use less than or equal to or greater than or equal to, then the points on the line are included. And you'll show this, you'll show that they're not included, you'll use a dashed line. And to show that they are included, you'll use a solid line. Okay. So this is the same line as we graphed before, so we know this equation to be y equals 1/2 x minus 3. If I asked you to graph the solutions that would make y is less than or equal to 1/2 x minus 3, you would graph this line. It would be a solid line because of the or equal to. So that means all the points on the line still work in this equation, just like they worked up here. All the points on the line make this equation true. But now it's all the points that are all the y values that are less than this as well. So here's one of the best surefire ways. You can get to the point where you feel comfortable enough where most of the time less than means underneath, greater than means up above, if you have the y here. As soon as the line gets a little too slanted, you can start to kind of, sometimes it's hard to determine what's above and what's below. It looks more like left side, right side. So if it's hard to tell what's below and what's above, then I would do a test point. Okay, so you check a test point to determine which side you're going to shade. Kind of like with the number line here, we could double check our answer by picking a point on either side. If we picked 0, because that's always easy to test, we put in 0 here, 3 times 0 plus 7, is that less than or equal to 1? You would get 0 plus 7, so 7 is less than or equal to 1. No, that's false. So 0 is not included, so all that side is not included in here. 0 was a representative point of that side of the number line. So we're going to pick a representative point. If 0, 0 is not on the line, that's the easiest one to check. Okay, so we're going to check our 0, 0 here to see if it makes this true. So I've got y is less than or equal to, so 0 is less than or equal to 1/2 times x, which is 0, minus 3. And we're just checking to see if this is true. You get 0 is less than or equal to 0 minus 3. You get the statement 0 is less than or equal to negative 3. And 0 is not less than or equal to negative 3. 0 is greater than negative 3. So this is a false statement. So 0, 0 does not work in the equation, and so we shade the opposite side. Shade the other side of the line. The line that does not include, the side that does not include 0, 0. So it's just a little bit of a coloring activity there. You get to shade on the other side where the solution is not. If 0, 0 worked, you would shade the side that would include 0, 0. Okay, so that's the basic idea there of solving and graphing linear inequalities, and we'll try some problems together on the bottom of the page where we'll start by just testing a solution. Pardon me. Okay, we'll see you at the bottom of page 1.